This question says, a 7-liter tank at 20.7 degrees Celsius is filled with 7.06 grams of carbon monoxide gas and 2.80 grams of sulfur tetrafluoride gas. You can assume both gases behave ideally. So essentially what we want is we want the mole fraction of the carbon monoxide and its partial pressure, the mole fraction of sulfur tetrafluoride and its partial pressure, and the total pressure in the tank. This problem is quite a lot of work. In the previous video on this playlist, I go through how to find mole fraction. Here, I have simply done that work already. So I've gotten the mole fraction of CO, which is 0.907, and the mole fraction of SF4, which is 0.0933. And I did that by converting grams to moles for each, and then taking the moles of CO in this case and divided by the total number of moles. Since there's only two gases, I did 1 minus the mole fraction of CO to find the mole fraction of SF4. Again, I go into this in great detail in the previous video, and I didn't want to spend the first 5 minutes of this video doing that. So now the new part. The new part is to find the partial pressure of each of these gases. There is more than one way to do this. I'm going to show you one of the ways. You may find another. What we need to do is use the ideal gas law. PV equals nRT. Pressure times volume equals moles times the ideal gas law constant times the temperature in Kelvin. Our goal is to solve for the total pressure, P. So this is going to be the total pressure is equal to nRT over V. Well, we have the total number of moles. I found that when I did the mole fraction, because I have to divide by the total number of moles. So I want to do 0.2780 moles as the total number of moles. The ideal gas law constant is 0.08206. That's liter atmospheres per mole K. I'm not going to write out the units because I'll run out of space. And then I want to put in the temperature in Kelvin. I'm given the temperature in Celsius, so I have to add 273 to this. And what I end up with is 293.7 K. I take all that and I divide by the volume in liters, and this is a 7-liter tank, so I divide by 7.000 liters. When I do that, I find the total pressure of both of these gases is equal to 0.9572 atmospheres. So this is the total pressure of both gases in this tank. Now, the pressure is being exerted by this gas. And essentially, if it's 0.907, that means 90.7% of the time that a gas hits the wall of the container and exerts pressure, it's CO. So 90.7% of this pressure is from CO. And only 0.0933 or 9.33% of the gas is SF4, so only 9.33% of the time when the gas hits the wall of the container is the pressure being exerted from SF4. Said another way, mathematically, the pressure of CO equals the total pressure times the mole fraction of CO. And this is called Dalton's law of partial pressures. In this case, that is the entire pressure, 0.9572. I forgot a 5 in there, so I'm going to rewrite that, 0.9572 atmospheres, times the mole fraction of CO, which I found previously, 0.907, and that gives me the pressure of the CO, which is 0.868 atmospheres. I can repeat the exact same thing for SF4. The P of SF4 is equal to the total pressure times the mole fraction of SF4, which equals the same 0.9572 atmospheres, times the mole fraction of SF4, which is 0.0933, which is equal to 0.0893 atmospheres. I now have all of my answers. This is the mole fraction of CO. This is the partial pressure of CO. This is the mole fraction of SF4. This is the partial pressure of SF4, and the total pressure is here. So I've solved all of these problems. This is quite a lot of work.